Welcome to the Materials Science lecture on microstructure and mechanical properties. In this session, we will delve into the intricate details of how microstructures influence the mechanical properties of materials. By the end of this class, you will be able to determine and draw microstructures that form upon cooling for hypoeutectic and hypereutectic alloy compositions. Additionally, you will understand how a given alloy's microstructure correlates to its mechanical properties. Let's predict whether more nickel completely dissolves in copper. Consider the atomic radius, crystal structure, and electronegativity of the elements involved. Use the answer selection bank to make your choice. Analyzing the dissolution of nickel in copper, we observe the atomic radius, crystal structure, and electronegativity values. The phase diagram helps us understand the solubility limits and the formation of solid solutions. Understanding phase boundaries is crucial. The primary phase forms above the eutectic temperature, while the liquidus and solidus boundaries define the regions where the material is entirely liquid or solid. Comparing hypereutectic and hypoeutectic systems, we see distinct differences in their phase diagrams. These differences impact the microstructure and mechanical properties of the alloys. At 240 degrees Celsius, the microstructure development of a 40% SN hypoeutectic alloy shows the formation of liquid and alpha phases. The composition of these phases is critical for understanding the alloy's properties. At 184 degrees Celsius, the microstructure of a 40% SN hypoeutectic alloy evolves, showing a liquid phase with eutectic composition and the formation of alpha and beta phases. At 182 degrees Celsius, the microstructure development includes the formation of primary alpha and beta phases. The eutectic structure consists of layers of alpha and beta, forming around the eutectic isotherm. Hypoeutectic alloys with compositions from 18.3 Wt% SN to 61.9 Wt% SN show various microstructures. These include microconstituents like alpha and beta phases, and the eutectic structure, which significantly affects the mechanical properties. For the SNPB phase diagram, identify the eutectic composition in the first solid phase upon cooling a hypereutectic alloy near the eutectic composition. Use the answer selection bank to respond. Analyzing the SNPB phase diagram, we identify the eutectic composition in the first solid phase upon cooling a hypereutectic alloy. This understanding is crucial for predicting the alloy's behavior during solidification. The microstructure significantly impacts the strength of PBSN eutectic alloys. Comparing different phases and their mechanical properties helps us understand how microstructure influences material performance. Equilibrium diagrams with intermediate compounds, such as the magnesium lead system, show distinct chemical formulas. These diagrams help us understand the phase relationships and the formation of intermediate compounds. In the copper-zinc system, equilibrium diagrams with intermediate phases reveal terminal and intermediate solid solutions. These diagrams highlight the formation of invariant points and the reactions involved. For the SNPB phase diagram, determine the number of phases in thermal equilibrium at various compositions and temperatures. Use the answer selection bank to make your selections. Analyzing the SNPB phase diagram, we determine the number of phases in thermal equilibrium at different compositions and temperatures. This analysis is essential for understanding the alloy's behavior during heating and cooling. Revisiting our learning objectives, we focus on determining and drawing microstructures for hypoeutectic and hypereutectic alloy compositions. Understanding the correlation between microstructure and mechanical properties is key. Phase diagram calculations and microstructures for a 40% SN hypoeutectic alloy at various temperatures help us understand the chemical composition and phase fractions. This knowledge is crucial for predicting material behavior. Thank you for watching. Please like, share, and subscribe to this channel. Add a comment below the video to share your thoughts and learnings. What did you learn from the video? What topic would you like to explore further? This presentation contains copyrighted material used under the Fair Use Doctrine for educational, commentary, and research purposes. All rights belong to their respective copyright holders. Links are provided in the video description to relevant resources.